All right, guys, today we're looking at Unit 9, Applications of Thermodynamics, and looking at Topic 4 within that, Thermodynamic and Kinetic Control. So we will look in terms of kinetics, so the speed of reactions, why a thermodynamically favored reaction might not occur at a measurable rate. So, kinetic control. So kinetics was our last unit, Unit 5, and we studied the rate of a reaction, the speed of a reaction. So reactions can be thermodynamically favorable, meaning that they will happen on their own when delta G is negative, but the products are not formed at a measurable rate. So it might be favorable, but we're not seeing much results, basically. And the reactions in this case are said to be under kinetic control. So what's controlling the reaction is the speed, not as much the favorability. So the ones that are under kinetic control, they tend to have a large activation energy. And reactions with large activation energies proceed at a slower rate. So when a reaction occurs extremely slowly, it does not mean that the reaction has stopped or reached equilibrium. It's just that it's slow. It can still be favorable, but just slow. So if a process is favorable and doesn't proceed at a measurable rate, it is reasonable to conclude that the process is under kinetic control. So that's when we have that high activation energy. Remember, we're seeing activation energy is from where our reactants are on our graph to the top of that hill. That's our activation energy. A catalyst, such as an enzyme in a biology or in biological systems, may be used to decrease the activation energy and increase the reaction rate. And however, this will have no effect on the favorability of the reaction, but it'll be occur faster. So if a reaction is favorable, it's favorable. That's not going to change. It'll happen on its own. But we could change how fast it's occurring by adding a catalyst. So if it has a high activation energy, then it's going to be under kinetic control. But if it has a lower activation energy, then it'll be more under thermodynamic control. So let's take a look at a quick example of what this looks like in a multiple choice question to help you answer this type of thing. So here's our example. We've got a chemical reaction, H2O2, that's hydrogen peroxide, like the stuff we have in our medicine cabinets, and it forms water and oxygen, and our delta G is negative. So the value of delta G for the reaction represented above implies the decomposition of hydrogen peroxide is thermodynamically favorable. So we know it's favorable, it's going to happen on its own. However, hydrogen peroxide is typically stable for up to a year stored in a dark bottle. So this is the stuff in your at 298 Kelvin. So in your medicine cabinet at home, it comes in that dark brown bottle typically, or black bottle, and they do that because light helps the reaction go faster. We don't want that. We don't want our bottle to just be water with some oxygen gas in it. And the 298 Kelvin is basically 25 degrees Celsius, which is essentially room temperature. So we want to know, why is this reaction favorable but so slow? How is it stable for up to a year? So the best explanation for this observation is that the decomposition reaction, we can say, is only thermodynamically favorable in the presence of a catalyst. Well, that's not true because it's favorable without the catalyst. We don't have a catalyst written in our reaction here. It says occurs when an increase in entropy, because oxygen gas is a product. So we want to know why it's happening so slow, but the entropy doesn't control speed here. The reversible, or it is reversible, and H2O2 is produced almost as fast as it decomposes. That's not true. We don't see a reversible reaction occurring up there. We don't have that reversible arrow. So it has a slow rate at 298 Kelvin because the activation energy is relatively high. That explains the speed of the reaction. All right, so having high activation energy tells us that the reaction is slower, and therefore that's why it can last for up to a year stored in that dark bottle. So the reaction has a negative delta G, so it is thermodynamically favorable and will happen without outside assistance. But the equation indicates that the reaction happens extremely slowly, or excuse me, the question indicates that it happens extremely slowly. This indicated the reaction is under kinetic control and then the activation energy must be high. So when it talks about a reaction being favorable, but it's not occurring at a very fast rate, then we want to look for an answer about the activation energy being high. So these questions, there's not a ton of them on the AP test or on practice tests. So we want to look for an explanation of why something is slow, and it comes down to that activation energy. So I hope that helps you with a few of those questions. And this is our last topic for this unit currently. Thanks, guys.